Every year, tech companies unveil a new piece of silicon for your pocket and mention they've packed 19 billion microscopic transistors onto a thumbnail-sized chip. We can wrap our heads around the billions of stars in our galaxy because telescopes and night skies help us visualize that vastness. But we have no natural way to grasp that same density when it's crammed into a device that fits in your pocket. To actually understand the engineering happening inside our everyday devices, we have to abandon our human perspective entirely and shrink down by dramatic orders of magnitude. It starts here. A person standing at an average height in a normal room, holding a standard smartphone in the palm of their hand. We're going to step away from this familiar world and move in the opposite direction, down toward the invisible. A 100 times shrink brings us to the scale of millimeters. From down here, the laptop's keyboard deck appears as vast as an apartment building. At this scale, we see the 1948 transistor. Compared to today, this is a massive assembly of clunky wires and crude mechanical parts. This chart tracks Moore's law, the observation that the number of transistors on a microchip roughly doubles every 2 years. To maintain that pace, engineers had to stay on a relentless schedule of halving the size of every component year after year. In these early decades, computing was a constant brute force war against physical space. Now we plummet another 10,000 times deeper into the micrometer scale. Here, a single strand of human hair acts as a 25-story cliff. This is the scale of the silicon found in the bulky desktop towers of the 1980s and the personal computers of the early 2000s. Standard physics starts to behave strangely at this depth. For instance, air molecules are now physically too large for tiny lungs to breathe. Even the wavelength of visible light is massive here. At this size, the world looks entirely blurry and wavy, as your eyes struggle to pick up light waves as tall as you are. Despite these obstacles, humanity built an entire industry of precise manufacturing within this alien environment. The final drop takes us to the nanometer scale of a modern 3-nanometer architecture chip. Individual atoms are now the size of marbles scattered across the floor. Now, obviously, or maybe not obviously, but 3-nanometer transistors this size aren't just built like other objects the way you might be expecting. Instead, we use photolithography. It's a process of projecting light through a microscope directly onto the silicon, developing a photograph on top of the atoms. This allows engineers to print billions of transistors onto a single continuous silicon wafer simultaneously. At this depth, the architecture is chemically manifested, etched into the silicon at the absolute floor of physical reality. To really grasp the density of those 19 billion transistors, it helps to temporarily flip the perspective and make things much, much larger. If we built a modern smartphone using the bulky glass vacuum tubes from 1946, how much space would those 19 billion components actually take up? To fit all that hardware, your phone would need to be the size of the state of New Jersey. If a single modern transistor were the size of a standard car, the smartphone housing all of them would be the size of planet Earth. That planetary scale infrastructure is currently sitting inside your pocket, running the video you're watching right now. This 80-year journey has taken the sprawling, room-sized complexity of the first computers and compressed it into a pocket-sized device. Now, to be honest, I don't really know how much longer Moore's law can apply to semiconductors as they get down to the literal atomic level. It's a staggering amount of density. One modern phone holds more engineered components than there are stars in the Milky Way. The result is a microscopic universe of human ingenuity, packed into a device we've learned to take for granted.